Hi everyone. I'm Tanvir Hossain, and in this tutorial, I will talk about a hands-on experience and like ways of power side channel attack. And if it is not familiar to you, what is power side channel, power and side channel attacks, everything, uh, no worries. I will start from very basic, like high school level basic, so that all the audience from general backgrounds, like from computer science to other engineering departments, they can understand what's going on here. So it will be easy, not like super uh, junk with math and everything. So let's begin. Uh, so a little bit of introduction about me. I'm like Tanvir. I'm doing my PhD. It's my third year of PhD, and I'm a graduate research assistant in Asta Lab, which is in Nichols Hall. So if you go to the Nichols Hall sometimes, you can visit our lab, and there are some cool equipments over there. I can show some experiments to you. And my advisor is Dr. Hawk, and together we are working on different problems of hardware security and assurance, like attacking hardware modules, um, microchips, and also protecting them from the future attacks. Okay, uh, let's talk about our agenda and outline today for this workshop. First, we'll talk about uh, basic hardware components that is useful for the side channel analysis. And then I'll see that I'll talk about how these components is useful to like emit some power trace or electromagnetic trace. Then how with different power models, how you can use those traces in a meaningful way. And then I will explain a simple power analysis with our chip whisperer setup. That it is a customized hardware setup for this kind of analysis. And then uh, I'll talk about how you can perform a real simple power analysis attack on real hardware. Okay, and then I'll talk about some cryptographic uh, algorithms. And it's not super complicated. I'll just talk about in surface level so that you just get the idea what's actually AES or advanced encryption algorithm is. And then after that, I'll perform differential power side channel attack, which is another kind of power attack, but it's more sophisticated than simple power analysis attack. So we'll perform DPA on AES algorithm, and you'll see that how you can extract key from a from an encryption engine. That's really cool thing. And if our time permits, I will show some other attacks on other cryptographic engine, which is called SCON. Okay, let's start. This is like the very basic, like high school level basic. What is voltage? So voltage is kind of like potential in a two port um, of a circuit. Like it's kind of like a potential of the electrons, you can say. And remember that. And then after that, we have another basic things in the electrical circuit, that is current. So current is just the flow of electrons. If you measure the how much electron is flowing, that's basically the you can measure and say it's current. So when you're like connecting any components with two uh, pole of a voltage difference, the electron will go through this wire, and you can measure the current. After that, we have another basic component, which is resistance. So resistance is just an a phenomena or an component that force or oppose the electrical current to stay like it just force the current to like you can say it just maintain the with a different resistance, you can maintain the flow of the current. So you can make it high, you can make it low, and you can also stop it with like a large resistance. So if you combine all of these, we have this like very basic law of physics, that is Ohm's law. That is which Ohm's law is saying that uh, in an electric conductor of 2 points, if you have a resistance, the flow of current is proportional to the voltage. So from this law is very important. Like we are using it basically everywhere in our uh, electronics and electrical domain. So from this law, we can we can do some maths and then we can get the power. So if you have a circuit like this with voltage and with a load, or any load is kind of a resistor. So if you have load, voltage, and if the current going through this load, some power is consuming, like you are getting some you are doing some operations, so the power will be consumed. And then you can derive this formula, which is P is equal to VI. And this is the power formulas. So now we'll talk about another component, which is super important. And we all have this transistor here and there, even in our phone, in our laptop, in our smartwatch, and everywhere we have these transistors. And this is the layout level or device level schematic of a transistor. But if you can actually mimic it, or you can represent this transistor with basic electronic components, that is the resistance, current, and capacitance. Now, and this is the basically symbol of transistor, what we use in our theories and like pen and paper. And using this transistor, we are making a lot of useful circuits, which are super important. Suppose this circuit made from 4 transistor, it is basically an AND gate. So if you have to decide, or you have to, suppose you have some conditions, and if you want to implement that in a circuit level, you should have this combinational gates, which will allow you to make these conditional statements. So this is basically the symbol of an AND gate. And now, see, to run this CMOS circuit, we call it CMOS circuit, complementary metal oxide semiconductors. And to run the circuits, you have to give some voltage potential difference in the VDD and the ground of these circuits, and then some current will flow, right? So if current is flowing through this CMOS circuit, and suppose you have a lot of transistors in this block, CMOS circuit block, and now for first operation, suppose 50 of your suppose you have 100 transistors inside this block, and in first operation, 50 transistors actually turned on and other 50 was off. So the current flow will be, suppose, 50 milliampere, right? But in the second operation, suppose second instruction, suppose you are first performed AND operation, and then you are doing a multiplication. For multiplication, suppose your 70 transistor switched on. So the current flow will be higher, right? So if your current flow is changing here, your power will change, right? So with different instruction you are running inside your CMOS circuits, the power is actually changing. The consumption of the power is actually changing. And if you represent it with time, like time dependent actually, because you are doing continuous operation. And this is the formula with like, it's like 0 to t time, how much time you measured for this analysis, and you can get the total power, or the time power with respect to time. So basically, it's just a graph which has an x-axis with time and y-axis is power, and you'll get some graphical representation of power consumption of the circuits. And see, this is also an NOT gate, like symbolic representation of the NOT gate, this one. And then if you do some operations, suppose if you are changing some inputs, you'll see that there are spikes with every change of the input. Suppose when you are going from 0 to 1, some of your transistors are switching, right? So you'll get some power spike. And also when you are going from 1 to 0, some of your transistors are also switching and you are getting a power spike. So here we have two transistors. Suppose you, in a real circuit, we have billions of transistors. So you'll get a like different power trace here, like not like this straightforward power trace. Okay. And another thing for this CMOS transistors, it has three types of, like, total power of these circuits are combined of three types. Like, one is static power, one is dynamic power, and another one is noise. So every circuit, every system has some noise. So we'll not talk about that. But static power is something when your circuit is idle, but still it is consuming some power. So if you just plugged a CMOS circuit with a battery and you are not doing any kind of operations, it's still leaking some power because of the property of the transistor. So that static power is not our concern. Only thing we will concern here is about the dynamic power. So dynamic power is the thing when you are switching the transistors inside your circuit. Okay, so with every switching, dynamic power actually changes significantly. The static power and noise are so negligible, you can actually ignore those things. And now we saw these little circuits like AND gate, NOT gate. And with this little circuit, we actually make some make flip-flops. And with all those flip-flops, we make like resistors. And with this resistor, we make SRAM, DRAM, and everything inside our chip. So if you combine all of these, use all of this, you will get something like this. So this is a real schematic of Intel Core i7 processor. And everything you are seeing here in this layout, it's all made from transistors. There are some wires, you can say, like, to connect, but other than that, all the device it has is basically made from the transistors. So if you plugged this i7 processor and with a battery or a power source, if you are running some operation inside your processor, and what you'll get, and if you probe it, what you'll get some changes in the power consumption, right? So suppose you are running Google Chrome in your computer. It will probably not takes like a lot of power. But when suppose you're playing a game in your computer, it will take a lot of power, right? So if you probe someone's PC or system, you can actually get an idea what that person is doing with his system. Okay, so this is how the power analysis idea came from, like from like very basic things. It's just like power, P is equal to VI, it's nothing else. Okay, any questions so far? No. And then, so, and this power things actually also called side channel. What is actually side channel? Side channel can be, here I talked about current only, right? Current or power is basically same thing. Like you can get it from the same way, but there another thing your processor can emit. What is heat, right? Like when you're running some simple operation, running Microsoft Word or Google Chrome, your PC will not get too much heated. But when you're playing a game, suppose GTA 5, what will happen? Like it's gonna be like heater, right? And so, and also the timing. There are timing difference of different programs. So with those, you can actually get idea about what's running inside it. And another uh, interesting side channel is electromagnetic side channel. So how many of you knows about Faraday's law? No one. Like left-hand rule of Faraday. So if your current is going, so there is one in another law is called Biot-Savart law. So if any conductor, if current is going through any conductor, conductor means this wires. So if any current is going through any conductor, what will happen? There will be an electromagnetic wave will be emitted in the perpendicular direction. Okay, that you can represent with also Faraday's left-hand rule. That is, if your current is going through this way, you will get some electromagnetic wave in the perpendicular direction. That means in this direction. So electromagnetic waves are everywhere. They're in everywhere. Like even if even like your mobile phone, your PC, every component that has current is emitting electromagnetic radiation. Like it can be less, can be high, but there are some traces over there. So if you collect those electromagnetic trace with sensor, you'll see that with the change of current. So basically when current is changing, electromagnetic wave, the radiation will be changed also, right? Because it is dependent to the current. So you'll see that with different operations in your computer or the system, the electromagnetic radiation is different. So you can get also information about that system from the EM radiation. And this is so useful because for the current and heat and timing, for these things, you need some physical access to the system. But think about EM radiation, taking the radiation. You don't have to probe the system from too closely, or you don't have to desolder any pin of the processor to get the power. You just have to have some sensors. You just have to go there like a little closer to the processor and you'll get the traces. So it's more convenient, but the problem is like you have to be too precise to perform any kind of EM attacks.
Basically, you can name or define side channel as side effects of running any
Yeah.
operation on
Yeah,
any kind of.
this is some. So in Oh, side channel is kind of like uh, what your system is emitting as byproduct.
Yeah.
Suppose you go to doctor, what your doctor will say after saying all your results, and probably like uh, when you go to doctor, if you have fever, what will doctor do? They see your test results, or they see your eyes, your skin, or if you have any rashes or not. So this is one kind of side channel our body is emitting, right? Suppose our temperature, this is one kind of side channel of our body. The rash, the skin color, eye color, these are the thing. Like skin color means like when you have some rashes, your you'll see that difference in normal state of from the normal state. So that will be another side channel of your body, you can say. So we all the system has side channel, like weather. Uh, it can be cold from the temperature of the weather. Someone can say that okay, now it's winter, now it's summer. So side channels are everywhere. So and now in this presentation or in this workshop, we'll just talk about power side channel or side channel that is just related to current. Okay. And suppose you have the trace, and what you'll do now, you have to convert that trace in something meaningful representation. To do that, we use power models. And that is first power model is Hamming distance power model. So it don't worry about this all those like definition things. The thing is that suppose in the first bit you have 0 0 for T0, like when you started the operation. Your input was 0 0, and then in the next operation it stays at 0 0. What will be the distance or Hamming distance? Hamming distance means the difference of bits and from one operation to the next operation. So here, it, anything didn't change, right? So it will be 0. But if your first bits are 0 0 and it goes to the 0 1, how many bits actually flipped here? 0 1, sorry, 1 bits, right? 1 bit. So here Hamming distance is 1. And if it goes to 1 1, then how many bits actually changed? 2. So think about it, like when it is 0 in the first state, and in the next state, it also 0, that means nothing is happening inside your circuit. That means you will just get static power. You will not get any dynamic power because anything hasn't changed here, right? But when 1 bit is flipping, you'll get some peak. Suppose 1 millivolt of peak. Yeah. But when 2 bits are flipping, it will be double, right? So from this thing, you can actually get an idea how many bits are flipping inside your circuit, right? So to do this, we use Hamming distance model. There is another model, which is Hamming weight model. Hamming weight model is basically you don't have to think about first stage or the next stage. Like if you are giving one input, and you'll see that in that input, how many bits has one. So suppose you're giving 0 0 0, it doesn't have any changes in the bits, so it's just 0. For 0 0 1, the Hamming weight will be 1. But if you're giving 0, 1, 1, that is if you're giving input as decimal value 3, the Hamming weight is 2. And for 7, Hamming weight is 3. So suppose you have 8-bit microcontroller, right? It can like handle 8 bits of data, that is 0 to 255, right? If you have this table with you and you get the power trace, and you have, suppose you want to guess about the input, so what you'll do, you'll see, analyze the power trace, that convert it to the Hamming weight model, and if you have this peak of 3, you will get to know that, okay, my input was 3. If you get the input of 1, like Hamming weight of 1, you'll get, then it is a bit trickier, because like Hamming weight for 1 and 2 is basically same. So you have to do some and other operations like correlation things also. But this is the idea of using power model to do side channel analysis. And this is a trace, real trace. Suppose you are doing multiple operations, same operation, but with different inputs. Suppose first your Hamming weight was 0, and then you increase the Hamming weights. So if you're, when you are increasing the Hamming weights, see the power, the trace here, the consumption of the power here is changing also. Got it? For 0, suppose it is here, and for 1, 2, 3, 4, up to 8, it is actually changing. Right. So this actually indicates how Hamming weight actually affect your power trace. Okay. So this is an useful information, because with this you can actually say which kind of data your microcontroller is, or your processor is handling right now. So if you take lots of data and do some statistical analysis, you'll see that with Hamming weight 4, the probability matrix will be like this high and peak. And for different, this means like this graph actually means like with different Hamming weight or the inputs, you will get different probability of on the trace. So this is actually distinguishable, right? If you get, suppose, having this peak, you can say that, okay, I have something in the input which has Hamming weight of 4. If you get this peak, you can say that, okay, it's 7, right? So now we can distinguish like inputs from the trace itself, like an unknown trace. If now I give you an unknown trace, you can analyze it, and then you can say what kind of Hamming weight it has, right? Or what kind of input it has. Any questions so far? Okay, so this is a setup for doing power attacks. So this is a customized setup. You can say it has a microcontroller, some other peripheral circuits, also clock signal, and here you can say that it is probing the input of the microcontroller. So it was not from my lab, I got it from the book. So just for reference. And you can say, okay, you are just doing it in a customized board. What about doing this kind of attack in real hardware or real devices? So there are another example where I also got it from another book. So don't think that it is from my lab. So in our lab we have some other sophisticated setup also, but this is I got from a book because I didn't have much time to replicate this one in the lab, and I didn't have a spare phone to do that. So what they're doing here is like they have a Samsung phone here, and it is connected to a battery, and in the in the when they're connecting this phone with the battery, they're also probing it through an oscilloscope. Okay, and then whenever this phone is booting or doing any kind of operations, you can see that different level of power consumption is happening. So here's the thing: suppose you started your phone, you'll see a lot of spike in the power trace because your phone just booted. So it started all the applications together. You will get a lot of spike, and it will stay idle if you are not doing anything. And then suppose you are giving the password for your phone, and for different password inputs, you'll get different kind of trace, right? And if you're doing if you're giving bad password or wrong password, the trace will be different. And if you're inputting correct password, the trace will be different. So from that, you can actually get the password uh, of this phone. I'll show you an example, implementation example of this kind of attack. Uh, any question? No?
So we need to have like compare a lot of password to find the different traces. And from the traces that we collect, we can like infer that the correct password might be this.
Yeah, you have to like not a lot of like not million
Okay.
but close to like you can get it from 200 sample to 1000 samples.
Mhm.
And who started it? Who started this power side channel attacks and like simple power side channel attack or differential power side channel attack? This man named Paul Kosher, this guy in 1998, he published a paper and he actually broke a lot of credit cards like Visa card, MasterCard, and other bank cards. So in your card, you can see that there is a chip. So whenever you are connecting that chip through a power, when it is booting, you can actually get information from that chip. And every chip has some encryption things inside it to protect your data from the outside world. So if you can decrypt or you can break that protection, you can actually get into the information which is embedded inside the chip, and you'll know that like important information about that credit card or the debit card, and then you're good to go to like bankrupt anyone. So he actually published the paper and the way how you can do perform a power side channel attack on the smart cards. And it actually like it was a new thing, but this is how all the like big guys and the rich people uh, actually responded like you never say a card is 100% immune. So even if you have now cards, it is not 100% immune. So yeah. This is a New York Times article. You can search it online and read it. And also the paper is easy to read and uh, super important for this kind of attack. And then in July, they broke actually DS, triple DS, RSA with this power side channel attack. And it was a big thing for previously it was just for the smart card, but now it was a big thing for both uh, like industry and also for the government because all the government data, all the secure channel communications are happening in with these encryption protocols like TS, AES, and other things. So if someone can snoop to this thing and they can actually get any kind of government data or sophisticated data from the system. So it was really a big thing for both government and industry. And now we'll begin with simple power analysis attack. So we're now done with basics and different models. Now we'll jump into the execution of the attack itself. Any questions so far? Let's start. So simple power analysis is simple actually. You just probe a system, you'll get some traces and you assume some like you get to know about the instruction, how many instructions are happening, how many attempt you have taken to give your password and everything. So it's just a simple, but with the SPA, you can do simple attacks, but you cannot break sophisticated encryption algorithm. That needs differential power analysis attack, which is uh, more complex and sophisticated to perform. And now to do that, we need some test bed, and it starts with capturing workstation, and it can be your laptop, your PC, and everything, which will capture the data, collect the data, store the data in a file to further analysis. And then you need a deep memory oscilloscope. What does it mean, a deep memory oscilloscope? How many of you actually deal with oscilloscope before you? You also. So oscilloscope is kind of like a machine, which with using this machine you can actually get to know about the power trace, voltage, current of any circuits or electrical system. So it's kind of like your ECG machine. Have you seen ECG machines? So when doctor probed your heart with some probing tips, they can actually see some graphs in the screen, spike in the screen. So if your heart is running correctly, they will see a pattern of spike. But if someone dies, the pattern is zero. Like they'll get a zero in that, like straight line in the graph. That means the system is not running. So oscilloscope, electrical oscilloscope is basically that one is also oscilloscope. We use oscilloscope to see the heartbeat or heart rate of our circuits. That's the easiest explanation. So to measure the power or the current or voltage of your circuit, you need an oscilloscope and deep memory oscilloscope, because if you are executing a big chunk of instruction, if you want to capture that, your oscilloscope should be capable enough to store all the traces with a lot of sampling points. So that's why we need deep memory oscilloscope here. And then we need a probing setup, which actually suppose you have a processor, you need to probe one pin. So you need some setup to probe the processor. And then stimulus generator where you give the inputs and power supply. And this is the device under test. So device under test is the target board or target device that you want to break or you want to get information from that device. And for our setup, we have chip whisperer scope, and this is a replacement of the oscilloscope and probing station. And we have a target board, which is an X mega target microcontroller. We'll run some operation inside this microcontroller and we'll probe it with chip whisperer scope. And we have our laptop here, so that's our like capturing workstation. So this is basically the setup. So this is the chip whisperer Husky. It and these two device 3 and 2, basically combinedly work uh, to get the trace. So giving the stimulus to the target board of this device 1, and then it takes a trace. It probes the target device and takes the trace and send back to the computer. And this is the target board. So when this little chip here inside this blue board, this is the main target board. We will run some instruction in this chip and we'll probe it with our power analysis setup. And you will see that with different instructions, different commands, the power is different. We are having different power. So this is the setup we have. Let's run a for loop first. So first, I just ran a for loop, and when I have for loop of 4, I have it is iterating 4 times. You'll see that this is initialization and these are the noise after the initialization. So if you look into this part of the trace, power trace, you'll see 4 patterns. Got it? But when I'm increasing the number of iteration, I'm having different power trace with 10 of these patterns. Isn't it interesting? So basically, you just know that, okay, how many iteration is happening inside this processor. Okay. So I just plotted the 2 graph, one after another, and you can see the difference with different iteration or different data, the power traces, we're having different power traces. That's all. Now, let's do something more interesting. Here we were doing like for loop with no operation. Suppose if I add no op and multiplication inside the program. No op means no operation. So when you give this command, no op command, to your processor, it actually, for every no op command, it stays as idle for 1 cycle. So if you have 10 no op command, the processor will be in idle state for 10 clock cycle. And I gave also 10 multiplication operation to perform in the processor. So the changes are distinguishable. See, when we are doing no op, there is little changes in the power trace. But when you are doing multiplication, the changes of traces is significant because multiplication needs a lot of power. to perform. And it in the future we'll see that multiplication is actually more clock cycles than no operation. Let's add more knobs. So to see the changes, if I add more knobs, like 20 knobs and 10 multiplication, see, like this part of the trace actually increased to here. So whenever you are adding more operations, your traces is telling you that, okay, user actually added more knobs or more multiplication. Okay. And if I add other instructions also, like adding knobs and then multiplication and then add operation, I can see distinguishable difference in the trace. No, multiplication is different. Multiplication is showing different power trace, and then again, knob is showing different power trace, and then add is showing different power trace. So from this graph or this power information, you can actually tell which kind of operation is happening. So it is a visual thing. Suppose if you take this data and make a database of your for your architecture. Suppose every architecture has their limit of instruction. It can perform this number of instruction. So if you have the power data for every instruction it can perform, right? What you can do, you can train a machine learning model with this data, right? And then in the real time, if you're probing some same processor or same model processor, uh, you can actually predict which kind of instruction is happening inside this processor or the architecture. So these are the real problem people are solving. Like they're attacking this processor or architectures with the power analysis. They are also trying to protecting the circuits so that they don't emit meaningful information. So here's the thing, like for multiplication, it needs 2 cycles. For add and no operation, it needs 1 cycle. I mean, can you say like why multiplication needs 2 cycle and add 1?
It's more complex operation in the CPU.
Yeah.
It's a different instruction for it. It combined. Yeah. I think it's a different instruction.
So in multiplication, it has some addition operation also, right?
Yeah.
Okay. So any questions so far about this or any idea how can you use it in real life or real world problems?
So I assume if you have like a encryption, decryption algorithm, and it contains a lot of operation like multiplication, add, addition, subtraction, XORing, and or you can really find out how many of these operations you have for each of the like this encryption, decryption. You can like assemble something, like put together something in order to get the key.
Yeah. Or the behavior of the program or like which kind of data it is processing, the secret data. Okay. And is there any way to protect these traces, like protect the CPU or the processor from emitting those traces? How can you do that?
One I can answer that question.
Anyone? You didn't understand the question?
Me?
Yeah.
I understand the question. I can answer it.
Anyone can answer. How can you protect your system from emitting this kind of traces, meaningful traces?
Have your system emit like fake traces?
Yeah,
Randomization. Yeah.
yeah, randomization. Like if you add more noise here, so if you will always have this trace, this will be there always. But if you add more noise here, random noise, what will happen? Attacker will not know which kind of operation it is doing because power, you are getting the power from the whole CPU, right? Whole processor. So it cumulative. So you cannot localized any suppose ALU operation or any kind of you're getting whole power trace from the CPU. So if it is running other modules also like random modules, which is emitting noise randomly, uh, the attacker will not know what's happening here. There are a lot of techniques like masking is another technique, derail or like like you can use two kind of execution path also to like multiple execution paths to perform same operation. So suppose for same multiplication operation, if you are using different circuits uh, randomly, what will happen? Attacker will not know which kind of operation it is doing because the every time it is changing the device or the circuit inside the processor, right? Obviously, it has some drawbacks like area. It is consuming more resources inside the processor, but to every security comes with some drawbacks and overhead. So, and now let's do a real attack. So, suppose you have a system, it is taking a password, simple password, and whenever you are giving the password to the microcontroller, it is actually comparing your input, user input, with the stored password it has inside it. So what it will do, suppose it is a 6-character password. First, it will compare the character 0 and then 1 and then 2, 3, 4, 5, right? It will do it in a loop, right? So if first character is correct, it will go to the second character and then third, fourth, fifth. But if your first character is not correct, what will do? It will not go to that. So loop will not continue, right? So this is the code, uh, just a simple password code inside the microcontroller. You can deploy inside the microcontroller, and then with the setup, suppose we are giving inputs. So suppose the correct password is this one, HOPX3. So with every character, when the processor is comparing every character, it is actually showing some traces, distinguishable traces here. So this is a 5 repetitive patterns. So you have 5 character password, and you can see that 5 repetitive pattern you are having because your loop is running 5 times, right? Now, if you give wrong password, what will happen? You will not get the same pattern like before because your loop next iteration is not happening, right? So now you can see that for the first character, we have this 5-character password. Suppose first we are giving age, which is a correct input. We are having red pattern, which is a correct pattern. But if you give bad character, wrong character, you are getting a random trace, which is not aligning with the um, correct guess. Suppose you are guessing. So for this 5 character, you are guessing. So whenever you are giving A, B, C, D, you will get to see that for A, it is not correct. You'll get some random thing. B, C, D. When you get to the H, what will happen? You'll get a peak or the pattern thing for the trace. So you can use this technique to break the whole password. But it is a long process, but still like useful for simple things like this little password. But if you are doing it with a cryptographic engine, which has 128 bits of information, 128 bits key, that is a long thing, and you cannot predict like every bits again and again. That would take a lot of time. So we will not do simple power analysis for cryptographic engines, but for this kind of simple password and snooping through this password, we can do simple power analysis attack. So here you can see that when you are giving H and X, and if you take two traces, this two trace, and get the difference, like the difference of these two traces, you can see that there is some spike going on here, like this one, right? But if you take H, like if you're giving the input as H, you'll see that this this spike is not here now because it passes to the next loop, iteration of the loop. Now it is waiting for the H node, like the second character. So every time you are giving correct input, that the difference here will be less, right? And you will get to know that which one is correct character, which one is not correct character. Okay. So we actually broke a system. We broke someone's password with simple power analysis now. I wanted to show this here with at least this experiment with the with my setup, but it doesn't have the space, and like you will not see from behind you guys. So if you're interested, please you can contact to me. You can come to our lab and see the setup over there. So any questions so far? Now I'll dive to the differential power analysis attack. So till now we saw simple things, simple like you get the trace, some 2 or 3 traces, and then you are like doing some analysis. But differential power analysis, like you'll take a lot of traces, and then you'll do some correlation uh, operations, like correlation calculation, to guess the key. Because here we did it manually, right? We guessed it by pen and paper, you can say, or seeing the trace itself. But for if you have a big key, like 128 bits of key or 256, it is not feasible to do it manually. You have to do some correlation operation to guess the key, right? So we'll do that here in the differential power analysis attack. Before that, I want to show you like where we are actually implementing this DPA attack. So main application of DPA attack is in the cryptographic engine. And what is this cryptographic engine actually? So we'll see some history of symmetric cipher. Symmetric block cipher means like a cryptographic engine which has same input, same key for encryption and decryption. And it started with DES, which is Data Encryption Standard in 1976. And so a group from Intel, actually, sorry, IBM actually made it. And kept it secret, like internal operation secrets, because they never wanted to give it to other people for their purpose. And then people used it a lot. They actually bought it from IBM. And in 1999, some people actually broke it. So if you have a system which is protected with DS, and if you tell those people, hacker group, that okay, if you can, I'll see that if you can break my system or not. They actually showed a method that they can break the system with in 22 hours and 22 hours 15 minutes. So it was kind of like a brute force kind of thing because DS was not that much protected at that time. So it was a big issue because every government data, secure channel communications like secure agency, also the diplomatic channel, everything was encrypted with DES. So if you see that people are breaking DES this much easily, it is a big issue for the national security and also the financial corporation and every other things. So NIST, which is National Institute of Standardization and Technology, and US government organization, they called for the proposal. Like they called all the scientists around the world to propose better encryption engine than from the DES. So people from all over the world submitted their proposals. And then finally, NIST proposed this AES Advanced Encryption Standard as a certified encryption engine for every kind of secure protocols. So after that, till now, we are using AES. And all the secure communication is encrypted with the AES. Have you ever seen your WhatsApp message that it is encrypted? So basically, WhatsApp actually use different algorithms. It uses AES also, but it has SHA 256 or something, and also it uses RSA maybe. But every encryption we are doing here and there, or in the agencies, government agencies, using an AES. So AES is a big thing. So with brute forcing attacks, you cannot break AES because the linear diffusion or the size of the key, it is too huge for the AES that if you want to brute force, it's gonna take like billion of minutes to do that, and it's not doable with the brute forcing because it has 128-bit key. So if you want to guess 128 bits, it should be you have to do 2 power 128 times of guessing. And this is not practically feasible with the classical computer we have. Although with quantum computers, you can do this, like you can break this kind of encryption engine. But with classical computers we have till now, we cannot brute force AES. So AES is like a symmetric cipher. It main thing is it has some 16 byte of like 4 by 4 state matrix. So it takes 16 byte data or 128-bit key or plain text and make it a matrix with 4 by 4 dimension. And every cell or the element of this matrix has 8 bit of data. So all these are combined 128-bit information. And it does all the operations with using matrix multiplication, matrix addition. So this is the algorithm in a nutshell for this AES. So we give the plain text or the text or the data we want to encrypt. We also give the key. So first it does the round key operation in the initial stage, and then subbytes, shift row, mix column, and then round key again. So this is one round of AES operation. So for every encryption, it does 10, 14, or 16, depending on the key size. Like it does 10 round operation and then generate the ciphertext for 128-bit key. So if your key size is 196-bit, it will do 12 round. And then for 256, it will do 14 rounds of encryption, and then you will get the ciphertext. So if you want to brute force or back calculate the text, it is not feasible or it is not doable, because a lot of time it is doing permutation and linear diffusion things that you cannot actually do it by any kind of classical computer we have. So first, it does the round key operation. So whenever you are giving the key goes to the key expansion module and it makes 10 round key. It has other separate algorithm for the key expansion. So now you have 10 different keys, which is generated from the plain key that you have given to the algorithm. Now for the first round, it will add the key with this matrix, state matrix. Initially, the state matrix will have plain text, and which is 128-bit. And then in the second round, we are doing subbyte. Subbyte is like you have information inside the cell of this matrix. You're replacing or substituting this byte with a predefined value. Suppose, for example, it has a S box. It is a publicly available S box for the AES. So suppose your matrix has 32. So it will replace 32 like this way. So for 3, this row, and for 2, this is the row. So when you're doing sub-byte operation, 32 will change to 23. So this is an operation. And how this S box coming from? It has different mathematics, different domains of mathematics to solve it. How the creator of this algorithm made this S box table. So that is called finite field arithmetic, and it uses Galois field 2 inversion to make this whole S box, and that's like a whole different complex level of mathematics they have done here to make this secure table. So infinite field and finite field. This is an interesting thing of mathematics. So whatever we are doing right now, we have the access to minus infinite to infinite numbers, right? We can calculate. Uh, Practically, you cannot do infinite number of calculation, but you don't have any field of limitation, right? To when you're doing, but in the finite field arithmetic, you have the limitation. You cannot suppose you have a circle, you cannot go beyond this circle, or you suppose you have a limitation of the number, you cannot go to beyond this number when you're doing some arithmetic operations. So Galois field is one kind of finite field arithmetic. Okay, after the substitution byte, then this algorithm will do shift row. Basically, it will shift the row in a pattern. And then it will do the mix column operation. So it just mix the column in a specific way. And then it will add some round key again, and you'll get the, after 10 rounds, you'll get the ciphertext. Okay. Now, see, we have two inputs here and one output, which is our ciphertext. Suppose you have given 128-bit image to the AES encryption engine, and it also has a key. What you'll get in the output, an encrypted image. So if you send this encrypted image to someone else, they should have the same key to decrypt it and get the original image, right? So this is how your communication protocols works. Suppose you are sending one image to your friend through WhatsApp. What will happen when you're sending your image? It will go through a port or protocol or a server, right? Someone on that server or the admin of that server, suppose Mark Zuckerberg, he can actually see your picture literally if you doesn't have any encryption algorithm inside it. So if you have encryption algorithm, what will happen? Throughout this communication channel, the image will be encrypted, and someone who is admin of that server will not able to see the image or the information you are sending to your friend. So whenever your friend is receiving the image, they will have the same key, and then they can decrypt it and see it. So with AES or any other encryption engines, you can secure the communication protocol. Also, when you are inputting your credit card information, your SSN, everything is encrypted, because these are some sensitive information we don't want to share with anyone in the server. So for differential power attack in the AES, what we'll do, we'll keep this input text fixed. We'll not change anything, because this is not our concern. We want to get the key. Breaking an encryption engine is like breaking the key of that engine, right? So if you get like breaking a phone is kind of like, it's not breaking the phone itself. Like you are breaking the password of that phone, right? So here is the key, is the password to get into this AES module. Therefore, we'll change key byte by byte, not bit by bit. Here, this is a important information here. And then we'll see how ciphertext is changing, and also how our power trace is also changing. Okay. And to do that, we'll have a computer or a system which will run the encryption engine itself. In this case, we'll have our target board, that is a microcontroller. And then we'll connect it to our PC and also through oscilloscope, which can probe it. Okay, so I can show you. So this is the target board we will use. So in this target board, we have a little microcontroller in the middle, and it has some setup with, with that we can actually probe the VDD or the uh, voltage, like power rail of this microcontroller. And then this is like this device here. Okay. And now we need an oscilloscope. So, and probing station. The thing is that you can get a microcontroller. You can get a microcontroller like this. You can make your own setup, like with complex probing system and with normal oscilloscope. But in the market, we can get this customized oscilloscope, which is solely made to connect these target boards to it. And this is acting as an oscilloscope here. So this is now the oscilloscope thing uh, from this diagram. And we have our laptop. So what we'll do, there's a port, you can just connect it. And there's a connector, you can actually connect this one and also some other connectors. And then with the USB cable, you have to connect it to the computer. So it's just simple setup. Now to implement DPA, you have to choose the intermediate result of the executed algorithm. So basically you need the algorithm, you need to know about the algorithm. So then you have step 2 and 3. Step 2, which is like measuring the power consumption, which we'll do with this setup here. And now, as we know the substitution by all the steps here, like from mix column to shift row to subbyte, suppose we have a trace from the real device. Also, for this step, we can actually make a simulated trace also, right? What is a simulated trace here? Simulated trace means it's like we'll give the same input that we are giving to the real hardware, but first we'll give it to a code that we have written. Like suppose you have the AES algorithm written in C or Python, you're giving the input, you can see in the output how many bits are changing, right? This is your simulated algorithm. Okay, so from this simulated algorithm, simulated data, you can actually get the simulated power model. Okay, suppose, for example, you have given 1, 0, 1, and in the output, you'll get 1, 1, 1. What is your Hamming weight here? 1, 1, 1, so 3, right? So, or for Hamming distance, it is 1, 0, 1, and it changed to 1, 1, 1. So Hamming distance is 1. So you will have simulated Hamming models with you, right? Then what you'll do, you'll apply same inputs to the real hardware and you'll get the power trace. So see, plain text will, can I see it from back? It's little bit uh, tiny here, like, but this is the plain text. We are not changing any plain text. We are changing the key. And as I said, we'll change it byte by byte, not bit by bit. If you want to change it to bit by bit, it's gonna be like huge, like like 2 power 128. So we'll not do that. But we'll do it byte by byte. What will happen then? First, suppose for the 128-bit key, you have 16 bytes, right? For 128-bit key. Suppose you fixed other bytes, first you change first byte, and then you get hypothetical power trace or the simulated power trace, and also the real power trace. And now you will guess with first one. So you'll give guess input, and you'll see that if your hypothetical power trace is matching with the real power trace or not. If it match, then okay, you got your first byte. Okay, but if it is not matching, the correlation will be different. Like it will not correlate. Like, so here we are doing some statistical analysis. That is like we are actually measuring the correlation of two traces. One is simulated, and one is our real harder power trace. So for the right case, those power traces will correlate. For the wrong trace, will not correlate, right? So still you can say, okay, you are still guessing. You're guessing not bit by bit, but still guessing byte by byte. But it is mathematically proven that whenever you are doing it byte by byte, your search space actually reduced significantly. Now our guessing the search space will be like 8-bit. How many combination will have? 2 power 8, which is 256, right? And how many how many bytes we have? 16. So it's a smaller number than 2 power 128. It's around 4056 or something like that. So with just 4056, you can actually get the whole key of the AES using this differential power analysis attack. Any question? And for the statistical analysis, you can use like different algorithms. There are different correlation algorithms available, like Pearson correlation algorithm or other correlation algorithm you can use. That's up to you, but it works actually. So this is the hypothetical part. This is how we do the hypothetical power analysis first. Like first we keep the input text and the sub byte key. The sub key means like 8-bit of the key, the whole key. We are giving it to the AES and having an output. And basically, it's just an XOR operation, and you'll get the output from this function, which is Hamming weight of the AES. And then we'll do the same thing to the AES real hardware, and we'll get the traces, simulated power, real power traces. After that, now we'll guess the byte by byte guessing. We'll do the byte by byte guessing, right? So see, if your guess is correct, you'll get a peak here. The correlation peak is high. But when the guess is wrong, the simulated power trace and the real power trace correlation is not high, right? So now you guessed 1 byte of the key, right? if you want to guess the other bytes, what you have to do, you have to just do the automation of this process, and your code will do it automatically. So now this is a key applied, and then with the after the analysis, it is showing that the retrieved key is exactly same as uh, the key we have given like in the initial stage of the AES algorithm. So we could retrieve or the break the AES successfully with this method. And that's all. Like I wanted to show it like uh, in the Jupyter notebook and like with the real hardware, but with this space and things, I think it won't be feasible. But if any of you are interested, please feel free to contact me. I can show it to you in my lab. And any question? And these are the all uh, references I have used here. And some of the figures, some of the diagrams are also directly taken from these sources. You just have to go there and see. And if any of you are really interested about learning power attacks, just go to this book. This is like the main textbook for this power analysis attack, and this is super easy to read. Like the author here, like he actually have written it like like for the high school students. So this is a really good book, I would say. Also, this GitHub repo, uh, it has a course book, some tutorials, also lecture videos and codes available over there. So a complete package for power side channel analysis. And these are the two references about Paul Kosher and his news 1998. And in this GitHub page, you'll have the whole process, step-by-step process of implementing DPA. And you don't need your data also. They already have that data uploaded. You just have to implement that code in your PC, and you'll see that you are retrieving their information. But if you want to change the key or the plain text and do the same attack again, you'll need the real hardware. That's all. Any question?
But I have some questions. So how does these methods, like how do you use them in your research while publishing a paper? Like, have you used this method to publish a paper already?
So these attack things are not new thing. Like people are doing it like for years.
Mhm.
This we are using these tools. These are kind of like tools or algorithms. We are using these tools to attack new encryption algorithms that hasn't been explored yet. So also you can use power side channel analysis for defense purpose also. This is attacking side I have shown you, but you can use it to defense purpose. Suppose, for example, there's an interesting project that we are doing in our lab. Suppose you have a sophisticated system. Obviously, you cannot do it in a large scale. You have to be specific, should be specific for any system. Suppose you have a system and it is doing some really important operation, and it is connected to a server or internet. Sorry. So as it is connected to the internet, someone can snoop through this processor and they can do some overflow attacks and other kind of software based attack, right? But how you're gonna uh, protect this system? Are you gonna like add another antivirus software or security software inside this processor? But that's not feasible also, because in a resource constant devices, you cannot add a antivirus software. Or even if you add a security software inside it, that software also can be hacked, right? So you have to protect it from the outside of the device. For that problem, what we can use? We can use either power analysis or electromagnetic power analysis. Like both are the same basically. So what you'll do, you'll continuously observe your system with the power traces, right? So when you know that which kind of program you are running in that system, so you know how your power will change every time for every instances, right? So if someone is doing some malicious activity inside your processor, what will happen? The power trace will be different, right? Your power trace will deviate. So if your control flow is deviating from the secure program to malicious program, that will be clearly visible in the power trace. In this way, you can protect your system. You can stop the processing, you can disconnect it, and you can actually localize where attacker attacked here, and which function or which data attacker wanted to steal, because you have the power trace or the forensic of the whole trace, and you'll see that which point attacker wanted to access. So this is one problem you can use. Also, there's an interesting paper I have seen recently. We are not doing it in our lab, obviously, but this is interesting that people used electromagnetic emissions or EM trace to detect drones. Because so one tricky things about drones are like often you cannot detect it with air defense systems. Like there is a certain limit. If you fly something like under this limit, height limit, the normal air defense system cannot detect it. So if you're flying your drone, suppose like few meters above the ground, normal air defense systems cannot detect that. So how you'll do it? So they actually implemented a mesh network with electromagnetic sensors at, around a perimeter. They collected those electromagnetic traces that the drone is emitting. So, and then they analyzed it that where actually this drone is flying, and also they could analyze that which kind of drone it is, like which vendor it is coming from, because every drone or every these systems has some unique ICs or unique uh, hardwares inside it. So if you have those data, you can trace them easily. So other operations you can do, all other research you can do with this power side channel, and because the problem is for the system, for a system is like you cannot protect your side channel with 100% efficiency, because there will be always side channel. Like you can make a super critical encryption engine, super critical, super secured uh, system, code or hardware, but eventually it will emit the side channel. And someone with proper knowledge about the system and the side channel, they can break it and get the information out of it.
Using like the lab, is there any efforts in the lab going forward to like research how quickly it can the task?
Yeah, we are doing it. We are using it. The problem I talked about, like monitoring control flow integrity using side channel analysis, we are using machine learning algorithms to do that. Any question?
If not, let's thank Tanvir for presenting it. Thank you.